Hello and welcome to the second session of our Aerospace Simulation Workshop by SimScale featuring EUROAVIA. Before we actually start to dive in our today's topic, I would like to make sure that for everybody the audio is working good. So guys, you will find a button in the GoToWebinar control panel which is called Raise Your Hand. Please press this button in the case you can hear me loud and clearly. Great, it seems that everything is working. In the case, however, the audio connection should drop while or during this webinar, you can also use our toll-free audio service numbers to access the audio of the session. For this, please dial one of these three numbers and enter when you ask the access code you can see above. Okay, guys, great, yes. Today we will take our first look into the field of structure simulation, and we will investigate the bending of an airfoil frame. And again, first of all, there will be a kind of crisp introduction to this webinar, especially because we have a lot of new people who joined this workshop series for the first time. After that, we will talk about today's topic. I will give you a short introduction into the role of structural integrity of the airfoil, and after that I will present you your homework and we will have time for question and answers. Okay, great. Maybe first of all, just allow me to introduce myself. My name is Milot. I'm working at SimScale as academic program manager, and as a part of this role, I'm also organizing workshops and webinars for students and people who are interested in a dedicated field where simulation can be applied. And the idea of this workshop is really to give everyone who is interested in aerospace industry a first hands-on introduction to simulation, and really the overall aim is that everybody who attended all three sessions and submitted his homework is able later on to use simulation for his own project and ideas. And therefore we cannot focus too much on fundamentals or simulation theory, but if you're interested in this field, there are a lot of other resources which you can use, and you can also qualify, as you know, for our free professional training, which will also cover these topics like simulation theory, etc. Just because a lot of people ask me the same question every time. The concept of this workshop is that we have in all three webinars. Every week, Thursday we'll have a webinar, so this is the second webinar. Next week we'll have the final webinar of this workshop session, and you can submit your homework. And if you submit all three homeworks, you will, as I mentioned, qualify yourself for free professional training and certification. And just because a lot of people asked, we will for sure record every webinar session, so you can also access it later on. And if you need support, just use our forum on simscale.com. We have there a dedicated section for this workshop series, and all your questions will be covered there. Okay, guys, then let's dive into our today's topic. And you may remember last week we talked about the fundamentals of simulation, so I gave you an introduction why simulation is used and where, and you also set up your first own simulation, which was covering the ventilation of an aircraft cabin. And in contrast to the aircraft cabin and its ventilation, which is very important, but not in any case really has a big impact on security, we will talk today about something which is very affected or very related to the security of an aircraft. We will talk about the structural integrity of an airfoil. And if you take a look, this is just a generic aircraft wing. You can see how it's made. So as you can imagine, having light wave structures is very, very important in aerospace industry, since in the end you're generating a lift with your wings, and you can only fly if the lift generated by your wings is higher than the mass of the airplane. I think that's absolutely clear. And so the main challenge when it comes to actually design or to the mechanical design of these aircrafts is really to make sure that you are as light as possible. And therefore, this kind of design structure is used in, I would say, every airplane or every modern airplane in the world to make sure that you have maximum stiffness and a minimum weight. So the idea is you use like ribs. And these ribs in the end are connected by stringers. And this creates a very strong structure, which is in theory very effective against bending and torsional load. And in the end, what you're doing at the end, you're putting just a metal skin on this structure, and this skin in the end is then the shape of your airfoil. And a big advantage of this design is it's not only very light and stiff, it also remains a lot of additional space, for example, where you can integrate the fuel tank. So as I know, in most of commercial airplanes, you will find the main fuel tanks in the wings. And today we will do, let's say, a very important kind of analysis. We will do a structure analysis and investigate the bending behavior of this structure for different loads and load cases. And here you can see the model we will later on investigate. It is made of several ribs which are connected with stringers, and we will only investigate now this internal structure without the skin. And what we'll do exactly is we will fix one side in all directions, so the side which is later on connected to the body of the aircraft, and put then a pressure load on the lower surface of the wing. You may ask yourself why on the lower surface. In the end, if you take a look at the wing and you really say you want to simplify it, you have a lower and a higher pressure region. But in the end, the force which is acting, or the pressure which is acting, is the pressure difference between those two sides. So if you have, let's say, in average 0.5 bar pressure on the upper side and 1.2 on the lower side, then you have a total pressure difference of 0.7 bar. And multiplied by the area, by the effective, let's say, area of this wing, the normal area, you will get approximately the overall lift force. And therefore, to simplify our case, we will just apply a pressure load, which is about the pressure difference on the lower side, and that will allow us to keep the number of boundary conditions later on low. But since this is a little bit more complex simulation compared to the simulation we did last time, I think the best is just to start with the demonstration, and then you can learn by doing. And there are just one or two things we should talk about before we start our simulation. You may remember last week I gave you a first introduction to fundamentals of simulation, and we also talked about the role of meshing within this process. So if we take a look at this metal cube, and you would just apply a force on this metal cube and fix this other side. And then let's say you have a displacement, let's call it U. And then you can use a kind of formulation which says the force here, which is called in red, is equivalent to stiffness multiplied by displacement. And for a lot of very simple examples, like a spring or this block, you can just, I think, really imagine what it means. That if you increase the displacement, or to increase the displacement for a given stiffness, you need a force. And the stiffness for some very equal examples we know from school maybe is just like a factor, which is depending on the material and the geometry. Now just imagine you have a much more complex geometry and you would like to apply the same process on it or the same approach. What would happen? Because can you just apply it like this? And the answer is not directly, but what you actually can do, just imagine you have this bigger object, real world object with even different loads on it. What you can do is dividing it up into a lot of cells, which is quite similar to the process of meshing for CFD. And then you can use these fundamental equations to calculate it for the whole domain. And instead of calculating then like stress or displacement for the whole body in one step, you would calculate it for each and every cell. And we have different kind of cells we can use. So we have hexahedral, tetrahedral, and pyramid cells. And all of these cell types can be used for divide existing complex real-world geometry into a simplified finite element model. Only difference is that right now on SimScale we are only supporting tetrahedral elements, which is not really bad because all of these elements have positive and negative aspects. And overall you can say tetrahedral is the best mix, or brings the best mix between accuracy, quality, and speed. As you can imagine, it's much easier to divide something into tetrahedral elements than into hexahedral elements only, or pyramid elements only. And therefore we will use only tetrahedral meshing in this course or later on. And for sure, again, the mesh size also has impact on simulation quality. Making your mesh finer will result in a finer results. And just imagine, here you have the same geometry with the same load case and a different mesh size. And you can really see that this has a big impact on the overall quality of your simulation. And here again, our overall aim is, when we talk about meshing, to get a so-called mesh-independent solution, which means that even if we would make the mesh finer, the change of the result would be so fine that we can say our mesh size is somehow converged. Okay, great guys, just this few words from me about fundamentals, and now let's really start to set up the simulation ourselves. Again, we have 3 steps, as I mentioned. First of all, we have to perform the pre-processing, which is mainly preparing the geometry for meshing, so simplify it and all the other aspects we talked about last week. If you're not sure about pre-processing, you should really take a look at our last week's recording. After preparing the geometry and meshing, we are going to set up the simulation itself, so we will apply boundary conditions, define which material this part is made of, etc. And finally, when our simulation is set up and solved correctly, we will use the online post-processor of SimScale to visualize our results and get insights. Well, let's start. Actually, that's the best to learn, as I mentioned. And yes, I just logged in myself on SimScale with my account. And here is a project I prepared which contains the geometry which I need for meshing. So let's open it, which will not take a lot of time because everything we're doing here is in the cloud. So all the data, the results, etc. are stored in the cloud, and all the computation is also done remotely. Yes, and as you can see, we have 3 different geometries here. We will only take a look at the first one right now for this demonstration. Later on, when we talk about the homework, you will see why we need these 2 others. And yes, here this is the geometry you can see. First of all, here in this area, you can see all important information about the geometry. So SimScale calculates automatically the bounding box diagonal length, which is in the end the length between the 2 points, the biggest distance between 2 points. And then you can also see the bounding box length in each direction. So your overall length in x direction is like 10.194 meters, in y direction 0.36052 meters, etc. And you can also see that we only have one solid, which means all these parts are one body and they are all connected. Which in reality, for sure, it will also be somehow, they will be connected. But the influence of this connection will be quite low, so we decided to merge all the parts to one solid, which will make our meshing easier. Yes, and first of all we need the mesh, and if you take a look at this geometry, we will fix this face and add a pressure load in all these faces here, which are on one plane. So I would expect right now to have a lot of stress in these areas where we have very thin walls, etc. But first of all, let's create a new mesh project. For this, click on this mesh item in the project tree, click on create a new mesh, and then you just have to choose the geometry you want to mesh. We want to mesh this wing with I-beam, and then just save. And now we can even add a new mesh operation. And you see you have a lot of different tools you can choose. Basically, as I mentioned, we have only right now we have TED meshing and hex meshing, and TED meshing is only available. Hex meshing is only available for CFD, so for fluid flow simulation, and we will use tetrahedral meshing automatic, which means we just specify the meshing type and the overall mesh size level. In our case, we will use a moderate, the number of cores, and the desired mesh order, and everything else like refinements will be calculated automatically by our tool. And here you may wonder, because you never heard about mesh order, and we will use a second order mesh, and by the way also 8 cores. And before we continue with our process of simulation generation, let's just quickly talk about second and first order mesh, and let me give you a very easy example which will help you to understand what we are basically talking about. So just imagine you have points, let's make them blue, and maybe use a, let's say you have one point, 2 points here, and between these points you have something like a function which you want to discretize in this here and here between these lines. And now let's use red for other kind of points, and let's just say this is a point of our mesh, a node. Let's put here also a node, and here too. And in the end, when we are talking about mesh order, it's the order of the function of our we use to approximate changes. For example, if you have a first order mesh, then you will use linear spline functions to interpolate this function by points. Which means if you have something like a complex function like here, if you want to approximate it the right way, you need a lot of points. And just by this higher number of points, your simulation will be able, or your mesh will be able to really, let's say, cover all changes fine. But there's also another possibility. Let's remove all these points. And just imagine you would use a second order function instead of a first order function. So not a line, but something like a curve. And then you would be able to use a much better result with the same size of points. And in the end, that's the difference between first and second order. And there are a lot of reasons for using or avoiding second order meshes. First of all, creating a second order mesh needs more time, so more computational time, is more complex and has a higher chance to fail in reason of problems with the CAD model. On the other hand, you will have a better approximation later on of the equations we use, so you will have better results, and it also can sometimes make it easier to solve complex geometries. And in the end, the reason why I would use a second order mesh for this is that later on you will see we will simulate a lot of stuff where we have a high bending of the wing and also very high stresses, and everywhere when you're going to simulate also nonlinear behavior, second order meshes will help a lot. So therefore we will do it like that. Just save our selection and click on the start button, which will start to calculate our mesh. And yes, let's just do a quick wrap up until our mesh is going to be calculated. So I basically showed you how to open a project and how to create a new mesh, and there we talked about different meshing options. We use automatic tetrahedral meshing with second order for the mesh and a moderate fineness to create a high quality automatic tetrahedral mesh. And there's some advanced topic we could not talk about today, but you can inform yourself very easily on our platform on the SimScale documentation. First of all, CAD cleaning and CAD repair can be quite challenging for real-world geometry. And if you're interested in this, I would also suggest you to take a look at the recording of our webinar with our customer Ben Lewis, which was like 2 weeks ago, and he gave a very interesting insights on how to clean how to use your standard CAD tool for model cleaning. And for sure, we can also do tetrahedral meshing completely manual, which is then similar to the setup of SnappyX mesh I showed you. But this is something you discovered in a lot of other older workshop recordings, so if you're interested in that, just take a look there. Great. As you can see right now, our mesh is going to be computed, but this can take up to, let's say, 10 minutes. And therefore, I already prepared everything here in a second project with the exact same settings, so we can take a look at the mesh here. Great. This is exactly the same mesh as you can see. We have the same base and the same setting, second order moderate 8 cores. And that's how the mesh is looking after computation. And you can really see that the mesh size was really automatically adapted to the geometry. And yes, the mesh is looking quite good from the point perspective view. And if you take a look here on the log, mesh computation succeeded, so everything seems to be fine. And we can even take a look inside of this mesh. So let's just create a clip. And let's move it for half a meter. just apply. And this can also take some seconds, because now everything has to be calculated in the cloud. Well, now we have a clip of our mesh here. And you can even take a look inside this mesh. Great. Well, the next step right now is to set up the simulation based on this mesh. And first of all, we click on this new simulation button, which will create a new simulation for us, and add all items we need to this tree. And first of all, we are now asked what kind of simulation you want to perform. Yes, it's a solid mechanics simulation, and then we have here a submenu, and we will do a static analysis, but an advanced one. And advanced means that we have the opportunity to consider also a nonlinear effects in this simulation. So we will put this option on true. And there are a lot of advantages. So we have using this nonlinear option, it will allow us to cover much more complex things which will happen when we put a load on this wing. And maybe here again, to understand the difference between nonlinear and linear, a very good example. And you may know this example from school. Just imagine you would have a kind of cylindrical probe. Let's make it gray, which is looking like this. And then you would put a force here and a force for sure also here. And then, let's say, here you have a cross-section of this profile. Then you can define, a stress. And then you can say your stress is force divided by area. And if you would now just use the machine for this and make a kind of test, where you have a stress and the displacement. So let's here say you have a length, and this is in the end the change of your length. Then, so what you're doing right now in the end, you are changing the displacement in both areas, and then you will have get a plot looking, sorry, like this maybe. And there you have 3 characteristic points. And in the end, what I want to say is, if you put a stress on something, or a force by the way, if you put a force on an object, metallic object, first of all, stress will become bigger and bigger, and it will look very linear. And this linear part, it was discovered with a standing simulation. And the definition in the end is that you are still in the elastic behavior of the material. But if you increase stress too much, then you will leave this elastic behavior of the material, and this is plastic behavior. So this is plastical, and this is elastic. And in this non-elastic area, if you remember, we said stiffness multiplied with displacement is F. And for linear analysis, we're assuming that K, our stiffness, will not change. But if we are going to this nonlinear areas, then the stiffness will change. And this is the idea of nonlinear analysis, that you consider the change of the stiffness. And this is what we're doing in the end when changing this from false to true. Okay, then we can click on save. Sure, we have to confirm everything. And yes, right now we can start to set up our simulation. Yes, and after we've defined what we want to simulate and which physics aspects we want to consider, we have to define which geometry, or to be more concrete, which mesh we want to use for our simulation. And yes, we have one mesh, which I will select right now, click on save, and then this mesh will be added to the simulation project and also added to our 3D simulation window. And now, yes, you can see the mesh here. I will change the representation now from surfaces with wireframe to surfaces only, which will make it more easier to see the different faces of this mesh. And right now, before we start to set up the physics or the boundary conditions of the simulation, we will do some preparational work. First of all, we create a so-called geometric primitive. The role of these primitives, or why we are creating them, is that I want to have a point here in the center of this face, of these two faces, to have so later on, when we are going to check the results, to have a reference point to measure the overall bending of the wing. And I've just extracted this point in my CAD system, and we'll just enter these points, and later on you can use the same points, or if you know, it's not necessary that you use exactly the same point. I just put it here because I think it makes a lot of sense. Theoretically, you could also use, for example, this point here, which is already existing. And something else I will prepare right now, and which is very important, is so-called topological entity sets. And these topological entity sets will help us later on to reduce our work, because they allow us to group existing surfaces to a kind of new surface. And then we don't have to select all faces again and again. And first of all, as I mentioned, we will apply our pressure load on the lowest side of the wing. So I will select all the surfaces here, which will later on be in touch with the skin, with the lower side of the skin. And I think now you understand why we are creating this topological entity set, because it would be a lot of work to reselect it again and again. So, especially for this very small features, it's really like a hassle. And this one is still missing here. And these faces too. Now it looks good. Let's zoom out to make sure no point was left, but basically I think that looks fine. Now just click on this new from selection and call it pressure load. Well, next step. The next step is to create a additional topological entity set for the site we will fix. By the way, I just saw I forget to select some faces because they need to be 20 at all. And that is, by the way, a very good trick how to change the sets. Just click on select. Then you can also select the missing ones. And then you delete this. Oh. And then you can create a new one. And what is also missing is our face we will use later on to fix everything, which is this one. So we will just click on the surface, and this is done. Great. You can see also two other points, the contacts and physical contacts, and they are blue, which means they are mandatory. In our case, we don't have to care for them because our whole model is made of one solid, and you only need contacts if you have multiple solids which can interact. So our next step is this material definition, and this is really easy in the end. What the meaning of this is here, you just define which material you want to use for your simulation. And you can choose between different behaviors. So we will use linear elastic since we will use aluminium for the frame, a special aluminium. And we have also a library which contains a lot of materials. It's a ready-to-use model, but unfortunately our model, which is called aluminium 2024, this is a standard material in aerospace industry, is not part of this library, so we have to define everything manually. So the Young's module is 73,100, sorry, multiplied and the Poisson ratio is 0.33. We have no creep, and the density is 2780. And you can find all these material values in material sheets from the manufacturer of the material. Click on Save, and now we've applied this material model to the whole structure. Next, we have to define initial and boundary conditions. It's a little bit similar like last session when I talked about initial and boundary conditions. In our case, we will not apply any initial or boundary condition, just let everything like it is, because we have basically no idea about the displacement and stress distribution within this model. We will directly start to define our boundary conditions. And we have two kinds of conditions. First of all, we have constraint conditions, and we have in the end only a constraint condition for our fixation. Everything is prescribed, displacement in all three directions, so we don't have to touch it. And we will map it on a phase set, which we just created before. And this is done. And next we will apply a load boundary condition. Let's call it pressure load. Type pressure is fine. There are also other types available. And instead of using a fixed value for the pressure, we will define a function which is 3.75 E4 multiplied with time t. And this is very important to understand what it means, because we are talking here about a pseudo time. It's not the physical time, you know, it's more the simulation time, which means that we can now ramp this value and investigate different loads with one simulation. For example, if we say t should be from 0 to 1 in 0.25 steps, in 1/4 steps, it will result in 4 different load cases. And now we can just click the Save button. And our simulation case is defined. Finally, we don't have to touch numerics, everything is fine. We'll just modify our simulation control. You can see our simulation interval is 1 second, and the time step length right now was 0.1 second, which means we would investigate 10 different load cases. Changing this to 0.25 will reduce the number of load cases to 4, which is also enough. We will also use 16 processors instead of only 4, and also increase this maximum runtime, just to make sure that the simulation will not be stopped automatically. And now the final thing we have to add is for the result control. So we will, or we can theoretically, we can add also different fields which should be calculated. So right now you can see which fields are calculated. And we will also add point data which should be calculated. For the displacement, just click here on Add New. Then we will call it plus displacement. And let's choose the Y component. And then we will choose the point we just created before. Save, click on Save. And now we are ready to run the simulation. We can just create a new simulation run and start it. Clicking on this button. Okay, let's do a quick wrap up. We talked about the general simulation setup. I showed you how to create a new simulation, how to choose the right type, and we talked about the difference between linear and nonlinear analysis. Then we assigned the mesh and created different topological entity sets. In our case, we created one for the pressure load and one for the fixation. We also defined the material and our own properties, defined the boundary conditions, and started the simulation. And since the calculation of the simulation can take up to half an hour and more, I have already prepared something, so we don't have to wait. And let me just open the project. Yes, and right now the project just loaded. Let's switch to the simulation designer. And here you can see a lot of other simulation I've created based on this geometry. But this is exactly the simulation I've just set it up with you. You can see it took 40 minutes. And when the simulation is finished, you will be notified by email, and you can see that this progress bar changed to green, which means 100% your simulation is finished. And once this is, you get this notification, you can just switch to the post-processor. And the good thing is, by the way, you can turn off your computer whenever you want once the simulation is running, and no data will be lost. So you don't need to have your computer turned on all the time to get the simulation results. And this is a simulation. We just set it up right now, and you can see we have now different things we can take a look at. For example, we can take a look at the residuum convergence plot, which just shows the maximum of relative and absolute residual for every step. And you can see the maximum absolute residual we have is 0.1 for the second simulation step. And relatively seen, it's smaller than 1e minus 6, so this is fine. And you have also the number of iterations, which is in the end just the steps we talked about, different load cases. And we have here what you can see on the point data, the displacement. And so you can see this is a displacement for the different four load cases. So the displacement at the first load case is 0.46 meter, displacement 0.9 meter, 1.3 meter, and 1.82 meter. Now let's take a look into the 3D simulation results, clicking on the solution fields item, which will open the 3D post-processing window. Okay, and now our results just loaded, and you can as you already can see, there's something is colored in the simulation. That's one of the features of our online post-processor, that automatically when the simulation is finished, SimScale is looking for a good way to visualize your results. So let's first of all step back, so you can see we are in the last time step. So for the highest possible load, let's maybe first of all switch back to the time step 0, which is our initial conditions, and therefore everything is blue, which means you have no stress. If you would update now the color bar, you can see it's really 0 here. And let's maybe first of all now go step by step. So let's switch first to the next time step. You can see something changed, and it's even out of range, so everything is red. We have to rescale our data range again. And now you can see basically this is our stress distribution. And as expected, we have the highest stress here in the area of the string, of this main string. And what you can also do is add a filter and use this wrap by vector filter. And right now what is happening is that we will visualize the displacement based on the displacement in each point. That's why it's called wrap by vector of this filter, because it's wrapping a new surface based on the displacement vectors, which can take some time because it needs to be calculated. And once this is done, we can right now investigate what exactly happened. For example, let's change the point of view to plus y or to plus z, sorry. And you can see now the displacement in total here. Now I will just turn off the color representation of the unwrapped body. And then it's very easy to see the displacement here. Let's put the color bar here. And what we can also do is, for example, go back to our wrap filter, and we can also jump to the latest time step. And then you can see this maximum displacement for the highest force. For sure, we can also change representation to, for example, nonlinear strain. Yes, and if you want, you can also save screenshots with our viewport tools. Great, then let's do on a final wrap-up. So I showed you how to change the time step and which importance is set related to the load case, and how to use the wrap by vector filter and to inspect our point data object. Additional topics, advanced topics, which are not covered today are again the derivation of additional physical quantities. So you could define yourself like a criteria you want to investigate and build a kind of custom solution field based on the results you have, like dividing one result by another or something like that. And you can, for example, also create plots within the 3D post-processor, and these topics, for example, are also covered in the professional training. And yes, since I'm nearly talking about 1 hour, I think you have some questions and you also want to know about this week's homework. So let's start with the homework. Your job will be this week to get into the role of a aerospace structural design engineer and to investigate 3 different designs for a wing structure and to investigate which of them is the best. And we have the standard configuration I just showed you before with this main stringer, and where we had this very big displacement, like more than 1 meter, which is absolutely horrible. And we have 2 other versions. One has added stringers, 2 here and here, and one has also added fillets, additional fillets, there, and there. And now your job is to investigate which one of them is performing the best for 2 different load cases. So you will investigate a more advanced pressure load case, which I just showed to you, and you will also add a torsional load case. And for this we have for sure all resources you need on one place. Again, in our forum, simscale.com/aerospace workshop, you will find it. And there you will find a project including all 3 geometries, a step-by-step instruction, how to set up the simulations, and also the recording of this webinar. And yes, I'm really looking forward to your submissions, and if you have questions or ideas, just let us know. By the way, for sure you can also create your own modification and simulate it and show us if this is maybe even better than one of the 3. Right, thank you very much. So right after that we will have our Q&A sessions. Thanks for being with us. It was very nice again. Have a nice evening and see you next week. Bye.